electrical inductance is a property of some components of electrical circuits, and to help introduce you to the quantity known as inductance, I want to remind you about capacitance and resistance. And then after reviewing capacitance and resistance, we'll introduce inductance. Now, inductance is a property that can be explained based on Faraday's law of induction, which we just covered in the previous unit. But let's get into our short review on capacitance. And actually, before I review capacitance, let me review something you probably remember from your study of Newtonian mechanics. A spring is governed by Hooke's law as long as the spring isn't stretched so far that it goes beyond its proportional limit. Within the proportional limit, the force exerted by the spring is equal to some constant of proportionality. We often call the spring stiffness, the K value, times the amount of stretch that appears in the spring. Sometimes this is labeled as delta x, but as long as we set x equals 0 as the equilibrium position, then there's no distinction between delta x and x symbolically. Well, why do I bring that up? I wanted to see if you noticed the comparison in this equation. For a capacitor, the voltage measured across, if I hook up a voltmeter from point A to point B, the voltage read depends on how much charge has built up on the plates. In fact, the voltage would be nothing more than the amount of charge that resides on the plates divided by the capacitance value. So here we have a case where force is directly proportional to position, and here we have a case where voltage is directly proportional to charge. Now you see a falling coffee filter here. In that case, the force acting on the coffee filter, well, there is no force when the coffee filter starts out at the top because the coffee filter isn't in motion. Very quickly, the coffee filter reaches a terminal velocity, and the amount of drag force acting on that coffee filter is equal to some constant of proportionality. We call it the B value, or the drag coefficient, multiplied by the speed of the coffee filter. This is equivalent to saying F equals a constant multiplied by dx dt. In the case of resistance, there's a voltage across the resistor. If conventional current flows clockwise in this circuit, then there's a voltage measured across the resistor, and that voltage can be explained in terms of Ohm's law. We can say V equals IR, or just as well we can say V equals R times I, but that's equivalent to saying the voltage is equal to R times dq dt. So here we have a force that's proportional to not the position, but the rate of change of position, and here we have a voltage that's not proportional to charge, but the rate at which charge is flowing. So maybe you're starting to see the analogy I'm trying to make. With capacitors, voltage is proportional to charge. With resistors, voltage is proportional to the rate at which charge flows. Now let's get to one more expression for force. Let's say you have a sports car at a stoplight. Then the force it takes to accelerate the car to produce a change in speed depends on how massive the car is. A big semi would require greater force to get the same acceleration as a small sports car. Anyway, we say F equals ma, according to Newton's second law. We could say then that F equals m dv dt. So are there circuit components? Well, here's one right here. This is our inductor, as opposed to having a resistor or a capacitor. Now we can talk about a circuit component known as an inductor, and here we're modeling the inductor in the form of a solenoid. In any case, there's a voltage across that inductor, and it's not proportional to the amount of charge. Inductors don't store charge. And inductors don't have a voltage across them anytime a current flows. In fact, if a constant current flows through this inductor, then there's no voltage at all. Nope, inductors are quantities that only have a voltage if there's a rate of change of current flowing through them. The equation we'll get to ultimately says the voltage across an inductor is equal to some constant multiplied by di dt, and that constant will give the symbol capital L, so that's our symbol for inductance. And it turns out there's a negative sign in this equation, and that's actually goes hand in hand with the negative sign in the equation induced voltage equals negative N d phi dt, which we recognize as Faraday's law. The negative sign here has to do with Lenz's law and the idea that induced voltages always point in a direction that tries to oppose the very change in flux that made them in the first place. Inductors are devices in electrical circuits that are always trying to defeat the rate of change of current. An inductor tries to level out currents and maintain steady values of current. So let's see, what are the units for capacitance? We measure capacitance in units known as Farads. And if we rearrange this equation, it says capacitance is charge per unit voltage. So a farad can be thought of as 1 coulomb per volt. Then we get to resistance. Resistance is measured in ohms. If we rearrange Ohm's law, we get R equals V over I, and we could say that 1 ohm is equal to 1 volt per amp. So what are the units for this quantity known as inductance? Inductance is measured in Henries. And 1 Henry must be equal to what? Well, let's rearrange this equation. The inductance in a circuit would be equal to voltage divided by rate of change of current. So a Henry is equal to a volt second per amp. So that's just a quick introduction. We'll explain in more detail the meaning behind this equation and the way in which inductors behave when placed in electric circuits.